Okay, so I'm going to go over this problem from IMC 2019. This is problem number 8. It says we have n real numbers, and we are selecting any subset of the indices. So any subset of 1 through n, and we are taking the sum of all of those elements with those n indices. And we're assuming that the function that maps every subset to its sum, to the sum of the corresponding real numbers, we are assuming that they take at least 1.8 to the power of n values. So we have 2 to the power of n subsets. Prove that the number of subsets of 1 through n, that S of I is a particular value of 2019 does not exceed 1.7 to the power of n. Okay, so which means it is less than or equal to 1.7 to the power of n. The problem seems a little bit awkward because we have these two weird numbers, which is not clear at all where they come from. And I guess my first reaction to a question is, why 1.8 and why 1.7? So part of the answer could be that, well, maybe 1.8 and 1.7 are somehow related. Now, is it that the difference is 0.1? Then where does the 0.1 come from? Or is it something else? Maybe, there's some reason that we have this 1.8 and 1.7, and we should have a reason for that. There's a reason for 1.8 and 1.7. One thing that I know is that if I change the 1.7 to 2 to the power of n, if I change 1.7 to 2, then the problem becomes silly. So the number of subsets that S of I is equal to 2019 does not exceed that becomes silly because there aren't more than 2 to the power of n subsets to begin with. So if I change 1.7 to 2, then the problem becomes obvious. If I change the 1.7 to 1.9, I still don't see how that can help. So there seems to be something about 1.7, which is just like a little bit less than 2. And if I change that to 1.9 or 1.99, I don't see how I can take advantage of that. I can see how that could help. So, but probably we would have to use contradiction. We're gonna have to say, because it says it doesn't exceed that. So let's see what happens if it does exceed. So let's see, you have these sets A1 through AM, that sum of AI is 2019 and M is more than 1.7 to the power of n. So we're gonna have to get a contradiction. Now, the other thing that I'm thinking is this 2019 just arbitrary, or does it have anything to do with 1.7 and 1.8? It could be completely arbitrary, but it could also have something to do with 1.8 and 1.7. So still, I don't even know anything about much about the numbers. That's like very mysterious. The numbers that they have given me, it puzzles me. That's if I can't figure out why we have 1.7, why we have 1.8, and why we have the number 2019, I feel like I should be in a good spot. I should be able to solve the problem, or at least like kind of come up with some good ideas. So if I have more than 1.7 to the power of n that satisfy this sum, so I would have to get a contradiction. So one natural contradiction would be if I can create subsets that have all different sums somehow, because they are talking about sums with different subsets with different sums. And at the same time, we know that there aren't more than 2 to the power of n sets. So if I can find sets that have 2 to the power of n, that have different sums, and there are 2 to the power of n of them, or more than 2 to the power of n of them, that would give me a contradiction. One thing I do notice is that if I take a set here, if I take, let's say you're taking x1, x2, x3, and then I'm taking a set, say x4, x5, and x6. And let's assume that S of that, well, I guess what I mean is that the elements of this, if I take the sum, so x4, x5, and x6, that's 2019. And let's say the sum of this one is something else. So there are a bunch of sets that give you different sums. If I add these, then I get different sums. If I take a set I1 and a set I2, and I take a set I that S of I is 2019, S of I1 is not the same as S of I2, then if I add them, S of I1 plus S of I, that's not going to be the same as S of I2 plus S of I. So maybe I can take a set here and the set this, and then take the set A2 corresponding to I2 and the set A corresponding to I, and then show that the sums of these two aren't really the same. And then somehow get a contradiction. So if I take pairs of sets, then maybe I can get a contradiction. There are a couple of issues that I see. First of all, there might be that there are elements that are repeated here. If I take elements that are repeated, so I take all of the elements that are corresponding to I, all of the elements that are corresponding to I1, and then if there is and if I do the same thing for I and I2, there might be elements in I1 and I2 that are in common. And then if I take the union, then those elements are going to be problematic, because when I take the sum, that those elements are counted only once and not twice. So that's going to be problematic. The second thing is, okay, let's do a bit of counting. So we have 1.8 to the power of n elements that have this different sums of this type, and 1.7 to the power of n elements that have sum of 2019. When I take the pairs of these numbers, I get, so let's see how many different pairs of these sets we have. So we get 1.8 to the power of n times 1.7 to the power of n, which is 3.06 to the power of n. And that's obviously more than 2 to the power of n. However, the problem is I don't know if these have different sums because of the intersections. So that's problematic. Okay, so I made some progress, it seems like, but I haven't really solved the problem. So how can I get rid of that issue? Well, I do notice that 3.06 is way larger than 2 to the power of n. So maybe I should use something that takes into consideration of the elements that are in common between A and A1 or between A and A2. And it also compensates for the fact that 2 to the power of n is way smaller than 3.06 to the power of n. Okay, so let's think about that and see how we can bridge the gap here. Well, if you think about this one, the way you can deal with this is by using multisets rather than sets. So what does that mean? Normally, if you're writing a set, this set and this set are the same thing. So these are the same sets, but they aren't the same sets. They aren't the same multisets. So essentially what we're going to do is We're going to consider multisets, meaning that every element can be repeated multiple times. And then we'll solve the problem. Okay, so it looks like we have a solution now. So suppose A1 through AM are subsets of, or should I say, okay, so let me just write it down the same way. A1 through AM, I would say sub-multisets of the set X1 through Xn, for which their sums are all, their element sums are all different. And M is at least 1.8 to the power of n, because we had that condition that there are at least 1.8 to the power of n of those sets. And also suppose on the contrary, B1 through Bk are sub-multisets of X1 through Xn, such that K is at least 1.7 to the power of n, and S of, or I guess the all BIs have element sums equal to 1.7 to the power of n. Okay, so first of all, consider these multisets. Consider the multisets AI union BJ. Okay, so there are at least 1.8 to the power of n times 1.7 to the power of n, which is 3.06 to the power of n of these pairs ij. Note that if AI union bj equals AI prime union bj prime, since since bj and bj prime have the same element sums, AI and bi prime must have the same element sums, which means I must be the same as I prime. So if I are the same as I is the same as I prime, that means AI union bj is AI union bj prime as multisets. And if they are the same as multisets, that means bj and bj prime are the same, or j and j prime are the same. Therefore, x1 through xn must have. So, okay, so here's what we're going to do. We're going to drop the x's and we're going to look at the indices. This must have at least 3.06 to the power of n sub multisets that each I appears at most twice. But every I has three possibilities. Either it doesn't appear, it appears once or twice. Thus, the number of such multisets does not exceed 3 to the power of n, and this is a contradiction. Okay, and that completes the proof. I think there's like one small thing that we have to make some changes here. So instead of using AIs, you would want to modify those as perhaps S of instead of those, maybe use S of I1 all the way to IN, and that would make it a bit easier to say, because multiset could mean that you're choosing X1 twice. So this needs a bit of a change in the wording to make it completely regress.